So good. So I want to take the discussion slightly different angle, but all related, obviously. So I have the pleasure of introducing a new technology vector. We've been working on resource-directed technology for a number of years. I didn't come up with this particular RDT. It's not, resource-directed technology. So what we've come up with is a set of new architectural features that basically allow you to carve out certain portions of the shared resources on the platform. So we have a number of shared resources in the platform, such as last level cache, memory, I/O, and we're actually slowly working on giving you the ability to partition those out and create sort of what we call the HOV lane. And we're applying that specifically today to network traffic. So that's kind of where we want to start. So I want to give you a quick overview, show you some proof points, talk a little bit about the software, and then summarize it. So what are the trends that are driving this transformation? And it's fundamentally things like network transformation and things like huge amounts of data growth, enormous amount of different kind of devices that are being hooked up to a network are basically forcing a transition for us. And what we're essentially talking about is, let me move this thingy here. What we're essentially talking about is a single architecture that can support a majority of segments. So things like the enterprise networks, communication services, cloud service providers, and then also obviously lastly the telecommunications equipment manufacturers. The way the trend is going in terms of number of devices that are being added and the amount of traffic that is driving, it is essentially at the crossover point where the amount of capital that they invest and the amount of returns that they're getting out of new customers adding and the data traffic that flows is essentially crossing, right? So they're spending more than the returns of the data traffic that they're getting, right? And that's a big problem. So the kind of stuff that we talked about, DPDK and the quick assist technology, all try to, we're all using that to create a vision that allows us to standardize on a single architecture, which will essentially allow us to address all the requirements of those segments. So that's sort of our really, longer term, broad vision to develop one architecture that allows us to do that. That enables a service provider or a comms equipment manufacturer, it enables them to actually take that platform, potentially combine it with an accelerator, combine that with an FPGA, combine it with whatever they need to sustain that business, and essentially run a standard piece of software on that to build that application to support that business. But think about it, right? When you start consolidating all these services on a single platform and look at a Broadwell platform today, so our V4 architecture, Xeon V4 architecture we introduced earlier in the year, you have on the high core count SKUs, there's 18 cores, 36 threads. Well, that's a pretty serious amount of processing power. You can sustain, people are loading up to 50 virtual machines on that. So how are you going to sustain 50 virtual machines, and then if you're now starting to consolidate a comms-like application on that, how are you going to sustain the performance for that single comms appliance, which previously was an appliance and now you consolidate it? How are you going to sustain the performance? And that's where the technology comes in, which we're about to talk about. So what we want to talk about is essentially combining an application that's latency sensitive, compute sensitive, might potentially require storage, and also requires huge amounts of throughput, right? How are you going to sustain that on a single platform? And that's essentially what we're trying to do with a new set of technologies called resource-directed technology. And when we break this down a little bit, when we start looking at some of the benchmarks, what we've actually seen for some work we've done with UC Berkeley, we actually seen up to 51% performance degradation as a result of combining these workloads. So if you take a comms workload and you start running this with a variety of other workloads, and you then look at the potential performance degradation that you can incur, we've actually seen as much as 51%. Right? So that's a big deal, right? And that breaks your sort of consolidation argument. So the point is, you really need these hooks, right, in order to kind of carve out the resources that you need. So another workload that we looked at was bzip. So a very common compression workload. You can accelerate it. That's all fine. But as soon as you start combining it with a number of other workloads, we actually see huge variance in that performance. So again, a reason why you want to be able to apply some form of quality of service in your platform. So the solutions that we've introduced on the current generation Xeon platform is something called cache monitoring technology, memory bandwidth monitoring technology, something called cache allocation technology, and then obviously it doesn't take a rocket science to figure out what we're going to put in that box soon. So cache monitoring essentially enables you to monitor the amount of last level cache a given application occupies. And this shouldn't be mistaken with performance monitoring. So we have these, we have a big block called perfmon. So perfmon enables you, we got 1,000 counters, and you might ask, okay, well, why do you come up with yet again a new counter? Well, this is slightly different. We're actually counting occupancy on a per application basis. So if you look at perfmon, typically very thread, very core oriented, right? So it's not, it does give you, it gives you metrics, gives you enormous amount of detail, but it doesn't allow you to make scheduling decision based on it. So this is fundamentally different in the sense that we give you a new construct. We give the Linux developers, Microsoft, VMware, we give them a new construct that allows them to make scheduling decisions based on this new data. And we give them a monitoring counter, we give them a memory bandwidth monitoring counter, and then lastly, you obviously want to be able to partition as well. So once you understand what your application's occupancy is in terms of cache, in terms of memory, now you can start making scheduling decisions. Now you can also make decisions on how much cache you want to allocate with a certain application. So the fundamental sort of tenets of the architecture is that it has to be flexible. So, and like I said, these are new hooks, right, that we've worked on over the course of a number of years. We're introducing them on the broader platform, and in order to use these, we want them to be flexible, meaning that you have to be able to configure them at any moment in time. So if you want to change the policy of of how much cache you want to associate with an application, well, then you want to be able to change that on the fly. So that's kind of what we mean. Sorry, that was the dynamic portion. The flexible portion means that we want to have a simple programming interface. So basically through model-specific registers. And this is a very easy way of reading and writing these registers. So basically read MSR, write MSR, very common blocks in any operating system. Secondly, it needs to be architectural. So you want to have it across every single, you want to have it supported by an instruction called CPU ID, right? CPU ID is an instruction utilized to basically figure out what your platform supports. If you don't have it in CPU ID, most operating systems won't support this because they have no way of detecting whether the capability is there. So we decided to make that interface architectural. It's a very key component within Intel as a whole to basically make these features available through an instruction called CPU ID. Very important. We have the software development manuals, which you can view online. Basically, these new instructions, these new features, they're all documented that as part of the architecture. And then lastly, it needs to be dynamic. So you need to be able to change you need to be able to change these registers on demand. So things like you detect that the occupancy of an application is changing, and you want to repartition the last level cache. Now you can use these MSRs to go and reconfigure the last level cache dynamically. So runtime, right? You don't want to do this one time because, like I said, this is to enable orchestrators and schedulers to be able to dynamically balance the platform on demand. So I won't spend too much time here, but the first construct that we're introducing is this construct of a resource monitoring ID. So a resource monitoring ID is today we associate the resource monitoring ID with either memory bandwidth monitoring or with cache monitoring, right? But as the shared resource monitoring feature set grows, we can continue to reuse the ARMID architecture to basically associate new events with. So today we only support 2 events, cache and memory monitoring, but going forward you can see more and more monitoring counters associated with this RMID construct. The importance is we can map them anywhere. So we can associate the ARMID with either a core or with a thread or with an application or with a virtual machine or with a container. It's a hardware construct, but in the scheduler we can associate it with any of these components. And that's really important because that makes it very, very flexible. Right? And then when privileged software goes and sets these up, it can basically utilize another MSR to say, okay, I've told the processor to go and monitor cache for this particular process for a period of time. At some point in time, privileged software can come in, utilize a different MSR to read back the occupancy of that particular RMID. Right? So let's say you set up an RMID for cache. Right? So now you run for a period of time, then privileged software comes in and says, okay, what was the occupancy of, or what is the current occupancy of this application in my last level cache? And then if that's big, you can go and make a decision and adjust that class of service, which I'll talk about in a second. So that's our RMIDs. So the kind of applications that will take advantage of this is things like perf, vTune. We're enabling orchestration software like OpenStack with these kind of capabilities, and we'll get there in a minute, and that'll make it more applicable to your field. So another really key construct we're introducing is the class of service. So class of service is a construct, again, is a hardware construct we can associate with a core, or with an application, or with a thread, or with a container, or with a virtual machine. So what you now can do is you can say, okay, a class of service consists of 50% of my last level cache. Now you can associate that class of service with an application, and when that application loads or runs or executes, it will only utilize 50% of your last level cache. Right? And we've built this into the scheduler. So schedulers such as the Linux scheduler, we're working with several closed source ISVs that are also enabling this in the scheduler. But if you download a current Linux kernel, you get this integrated. So basically when you utilize perf or you utilize C groups, right? When you set up a control group, you'll get a new control group, basically a cache allocation control group. When you associate your application with that control group and you've said, okay, this control group maintains 50% of my LLC, then when your application executes, only 50% of your LLC will be used with this application. Does that make sense? Yeah? Right, so we've been working with a number of proof points that'll kind of paint the picture a little bit better what these hooks are all about. So we've been working with UC Berkeley. A number of researchers are actually concentrating on edge devices. So they've been basically moving a set of applications. They've been also working on a virtual switch, but they've been taking a number of virtual machines and basically integrating communications devices in those. So things like network address translations, things like Snort, which is an intrusion detection system, they've been virtualizing that and then basically optimizing them and monitoring the performance associated with that. So when they ran various of these virtual machines side by side, and this is where that first data point came from, what I quoted earlier on, on the network address translation application, they incurred up to 51% performance degradation when they were running several applications in parallel with that application. So this is an indication that network address translation, or at least this version of network address translation, is very cache sensitive, right? It's basically obliterating the LLC, and it's causing so much pollution that all these other applications, right? Or actually, let me paint it slightly different. So the network address translation is very dependent on a portion of the LLC. And if other applications come in and cause evictions for that network address translation application, you basically incur a lot of performance degradation. So what we proposed is, well, why don't you take Snort, or why don't you take network address translation? Why don't you partition it? Right? Why don't you take a small portion of the LLC and make it uniquely available to that application? And that's what the class of service construct allows us to do, right? So we associate, a very small percentage, about a tenth of the last level cache, and on this particular part, it equals to about 5 megabytes of the LLC. This is 45 megabytes LLC on this particular Xeon server part that we benchmarked on. So we took a very small portion of that, made it uniquely available to that particular virtual machine. And then your variation for at least network address translation goes down to 0. Snort still incurs about 2% variation as a result of it needing memory bandwidth, right? Because, here is the key, right? If you restrict an application to a small portion of the LLC, and it has a big memory footprint, right, or a big cache footprint, it will exceed that small portion of cache, and it will put pressure on the memory interface. So it's pretty obvious what you need next, right? If you want to build a full, quality of service, enabled platform, you obviously need to fix the second order of contention, which is likely your memory interface after you restrict the amount of cache that a certain application can use. So the last little bit of green that you see is very likely because those applications start exceeding that small portion of the LLC that we associated with it. Now, another thing you could do is essentially build a control loop. You could essentially say, hey, and I'm going to monitor you. I'm going to monitor the application that I really care about, and then dynamically I'm going to grow and reduce the amount of last level cache it gets. And those are the kind of things we're building right now with things like perf and control groups, with OpenStack and other sort of schedulers. So that's sort of our next set of kinds of applications and intelligence that we're going to build into the scheduler.
How are you scheduling the individual apps on the per core basis? Because you're running each of those applications on per core, but who schedules that? Yeah,
sorry, I need to rush really fast through this. So here is how we actually do that. So when I say scheduler support, that is exactly what I mean. So that ARMID and that class of service construct, we've built that into the scheduler now. So we have when you say perf, go track for me this particular process, then perf associates an ARMID with that process, and any time when the scheduler goes and programs up, and when the scheduler goes and schedules your application on any core, we make sure that our hooks program up the ARMID with that particular core. Same for the class of service. So if you have an application, for instance, in this particular case, right, we say, okay, this particular virtual machine is getting this portion of the LLC. This portion of the LLC is described in the class of service. That class of service gets poked in this model-specific register, and the scheduler does this at the time when you schedule that virtual machine. Does that make sense?
It does.
So no matter where you schedule it, like I said, these MSRs are dynamic. You can program them anytime, anywhere. Right? So when the scheduler reprograms the cores that it's going to go and schedule the virtual machines on. So for instance, it migrates it from core 6 to core 9. The scheduler puts the virtual machine on core 9. Then we will make sure then the scheduler also sets up the registers in such a way that now that particular core associated with that virtual machine only fills in this class of service. So this is really important because in order to get these kind of changes into the Linux scheduler and get accepted by the community, it can take up to a couple of years.
Yeah, you probably have to be very proactive about publishing the metrics that you're
Huge. Yeah. Huge.
How are you doing that? Because you guys have a framework called Snap that publishes telemetry on a multi-host perspective. Obviously, this is pretty single host. Are you integrating there?
Working with Snap to get these hooks integrated. Now, I'll get there in a minute.
Oh, okay, cool.
So really, but it's very important to understand that this is the plumbing that you need in order to go and do this.
Yeah.
So we're still at very early stages where we got the plumbing done. But now it's time to kind of up-level this and get this into the right management stacks. And I'd love to have some feedback from you what that is. So Snap is one of them. Control groups is another. OpenStack, Nova, whatever their management stacks are. Where do we go with this? It'd be great to get some feedback from this group of developers here.
Yeah, because just like selfishly as a developer, like I've been learning lately about how to write code that's mechanically sympathetic. It's not my term. It's this guy, Bill Kennedy, he's a big guy.
Right.
Love his talks. Anyway, this kind of data is like really valuable to somebody that's trying to write code like that, because you might not know. You might not know that you're violating some, caching, doing a cache miss with some of your code. But this really provides that insight.
Exactly.
Well, HPC programmers, the guys using supercomputers would love to know how much of their reads and writes are missing.
Yeah.
Yep.
Being able to stay in.
So this is really cool. So perfmon, right, and it might be an unknown term, but gives you that. But it's so incredibly hard to use and so incredibly hard to integrate into your code that only vTune users use it, right? Mm-hmm. These hooks They give you a number that says, okay, your application is consuming, 15 megabytes. You can make a decision on that because you know very easily that your cache is 45 megabytes big. So you're consuming a third of your LLC at any moment in time, right? So now you could even some of the applications which we completely didn't expect obliterate your LLC. Now it's very easy to make a decision on that, right? Yeah. And also the counter argument is that okay, we'll give you occupants, and that doesn't mean whether that data is valid or not valid, right? So that's another reason why these perf mon counters have a very good reason for being there, because they give you all those metrics. They give you insight exactly what's going on. But if you want to make scheduling decisions, you're not going to take 10% of overhead for running a perf mon application. You're not going to take that, right? You're going to take an occupancy number that says, okay, you're in the ballpark of 10 megabytes a bit, give or take. We do set sampling. You might be off a very small amount. But we're very accurate in the sense that you can make a scheduling decision based on this number. And that's fundamentally what we're trying to do here.
Yeah.
So.
And with the resource allocation using C groups, this is claiming your space and making sure nobody comes into that.
Yep.
So it's not just when I need it, I get it. It's actually reserved.
Yep.
And
yeah. So, and there is also a counter argument to that, because the real estate for last level cache is very expensive.
Oh, yes.
Right. So now you carved out an area that you could potentially cannot use if your application isn't being scheduled. So that's why you might want to have overlapping control groups, or you might want to dynamically scale them with these feedback loops and that sort of thing. And again, this is where we're looking for feedback from a users group, right, and from a development group, rather than us making things up as we go along, right? We can't build the end application because we don't necessarily know how this will be used across a large developers group.
Right. But there's definitely applications where you can't provide enough LLC, period.
Absolutely.
And then there are some that needs to stream the data so fast that it could, as long as it had a dedicated 25%. I'm making up that number, but I mean, analysis will tell you what that number is. If I had a LLC 25% all to my program, then all of a sudden I get all this efficiency out of it because I'm leveraging that cache and I'm not worrying about these random processes swashing all over.
You're spot on, but we want you to make that choice. We want to give you the tools for you to be able to make that choice. And that's the difference here, that we want to be able to make changes dynamically as you need them. And if you're in a service offering business, you might want to set that video streaming virtual machine of a non-paying customer to the side for a second while you serve your customers that are paying, right? That's kind of, what we say.
Or basically go ahead and limit their resources so you can give those resources to the other people.
Exactly, exactly. Yeah. So that's essentially, and sorry it took a while to get there, but I have to set that baseline a little bit to see where we're coming from. So very good feedback. So previous numbers were very much throughput based. This is all latency. So now it's along the same lines. We're actually going to see what the response time is of these virtual machines, and they equally improve versus the throughput. So AppFormix is a startup company we've worked with quite a bit, and they're taking it a step further. They're enabling a Kubernetes-based management engine where they basically have insight over a whole group of servers. This is a distributed management system. And they're basically looking at, okay, what are the noisy neighbors in my platform, and how can I protect myself from that? And they have the same sort of thing. This is non-accelerated. This is using the ASNI instructions, where they're basically saying, hey, we can make the throughput go up, we can make the average response time come down, and we can make the worst case response time come down. So in terms of networking, virtual switching is becoming very, very important to us, as all of you know, right? If you look at any big data center and they're running virtualization, it's very likely that they run some sort of a virtual switch, whether it is Xen, whether it is KVM. Everybody utilizes one. What we actually found was that in some cases, if you dedicate if you run a virtual switch standalone and you push a certain amount of traffic into that. In this case, we had a large number of cores, but we capped it at the ones that we wanted to go look at. So when we see that we obtain about 5 megabytes of last level cache in this case. So that's the kind of metric that the monitoring capabilities give you. And again, you can make decisions based on this data. So you see that you have and this was pretty static. So we had a relatively small routing table, and it would maintain about 5 megabytes worth of LLC. We actually wouldn't incur any memory bandwidth because the routing table was sufficient size that we didn't need to go to memory. When you then start running some other compute and storage-based virtual machines, you actually see that we incur significant amount of performance drop, so up to 66%, all as a result of our virtual switch getting kicked out of the LLC. And then you also see that your memory bandwidth for this particular core goes up significantly. So we're up at 2.3 gigs, and that causes huge amounts of performance degradation. So what we do is we carve it out. In this case, we took a substantial portion of the LLC, 50%, and then we get our cache back, and automatically our performance is sustained. So the hooks work as they intended are. So wanted to spend a minute on software, but they're not going to allow me. So.
1 minute.
Oh, very good. So these are the current scheduler-enabled solutions we have. So we have perf C group. We're working on a concept called P groups. Would love you to take a look at it. It's just posted on LKML. So you asked earlier on what is your method for feedback. It's right now mostly LKML, and that's largely because we need these scheduler hooks in the kernel, and that is the base plumbing. It is a must to actually get this whole thing rolled out. So we also have an application that we develop internally, and that's basically that screenshots that are shown earlier on. Those come from this particular application. It's like a top, Linux top-based application which we kind of use for monitoring memory. And then another portion we've been working on, and it's pretty obvious, but what we do is we have for those folks that are familiar with OpenStack, we have an alarming engine that this is all prototyping. This is very early stages. We basically have a Nova together with the policy engine, together with an alarming engine that monitors a whole bunch of hosts. And when there is a certain policy that is being violated, we will on demand, basically move that virtual machine to a less loaded platform. Bunch links, and then I was going to wrap it up. But you're going to do that for me. So.